Welcome everyone. This is on .NET, a weekly discussion with the .NET team and guests. And this week, I'm very happy to have Aaron on the show. And we're probably going to talk about AkkadNet, but why don't you tell us what you're doing? What are your various projects?
Sure thing. So thanks for having me on the show, Bertrand. And so my name is Aaron Stannard, and I'm the CTO and co-founder of Petabridge. We're a company that helps .NET companies build highly available distributed systems using .NET open source. And the open source projects that I'm really heavily involved in, AkkadNet's the big one. So it's an implementation of the distributed actor model in .NET. I also am very heavily involved in .Netty, which is a port of the Netty sort of socket server library. On Java, it's the library that powers the internals of Apache, Cassandra, and a bunch of other really big Java projects. And I also have a project called EndBench, which is an automated performance testing library that we just published back in November. So that's sort of what I'm up to. I've got my fingers in a lot of different projects at the moment.
So is it fair to say that most of your open source activity is actually entirely related to your day job?
Excuse me?
So you talked about your day job and you talked about your...
Oh, my day job. Gotcha. I thought you said my data. And I was like, well.
Oh, sorry.
Yeah, most of my open source activity is related to my day job, but it didn't start that way. Mm-hmm. Originally, what originally got me into open source was actually I worked at Microsoft as an evangelist for a couple of years. And in particular, I worked on Windows Azure right when we were adding support for Node.js. So this is before infrastructure as a service and Azure websites were things. This is like 2011, 2012, that time frame. And so I got really involved in the Node community there, and I got more sort of used and familiar to having to incorporate open source projects and report issues back and use the GitHub workflow and you name it. And then I left Microsoft in 2012 to go and start a Windows Store and Windows Phone and eventually Windows Desktop app analytics and marketing automation company called Marked Up. And so that was a really a big data application. We had at our peak, would have something like 500 megabytes of event data per second we would need to process sort of coming in through our API. And in order for us to build our marketing automation product, we actually needed something like Akka on the JVM in order to do that. It's essentially the way that system was architected was we would have to go and evaluate streams of data for hundreds of thousands of concurrent users. And every single app would have multiple different campaigns, and every single user would have different events that were specific to that app. And we had to find a way to go and very quickly turn around decisions on whether or not this user should receive this message or this other one, or maybe they should receive this message in a day, whatever. And for most of our customers, the thing that we found was that in order for that marketing automation product to be effective, we needed to be able to render a decision in under a couple of seconds, regardless of how big the load was. And the difference between sending someone an offer right there when they're looking at maybe buying an in-app purchase or something like that versus 30 seconds later was like an order of magnitude decrease in throughput, or not in throughput, in conversion. Yeah. So it's like the difference between selling 40% more in-app purchases versus 4%. So so I got involved with AkkadNet and Helios, which is sort of the predecessor technology to .Netty, another socket library based off Netty. I got involved with doing both of those to try to get that project off the ground. Prior to that, we've been involved in...
You weren't a founder of those projects.
Yeah. I co-founded AkkadNet with Roger Johansson. And so he and I sort of were working on our own separate Akka implementations in .NET right around the same time. And then I found that the benchmarks of his project kicked the snot out of mine. So I went ahead and ditched my at-core Akka implementation. But what I brought with me, though, was all my networking infrastructure to build the distributed parts of it. And so we teamed up on that. and eventually changed the name of the project to AkkadNet once we got permission from TypeSafe, the company that's behind the Java version of Akka.
So it's not a direct port of the Java code then.
It's a direct port of the Java code, but it's all written by hand. So we're not using like an automatic translation tool or anything like that. And the reason is that even though it's a direct port, all the APIs in Akka.net, we attempt to match them with what's in the JVM because they're, JVM and the Akka implementation on the JVM has been used in tons of enormous applications. Twitter, LinkedIn, Walmart are all very heavy users of it. Apache Spark, which is the big thing that's sort of killing Hadoop now, uses Akka cluster internally. So there's a lot of validation of how that design works in production already. It's probably the most heavily used actor system implementation in the world. And so we wanted to try to leverage their hard-earned lessons in our own design. So that's the primary reason why we chose to do a port rather than trying to reinvent the wheel, so to speak. But we do try to stick with idiomatic C# and F#. There are some concepts that, for instance, my opinion, Java and the JVM in general does a fairly poor job with generics. And there's other types of concepts that .NET simply does better. On the flip side, there's some concepts in the JVM that are very difficult to express in .NET too, but that's sort of beyond the scope of our podcast today.
I don't think it is. Actually, I'd be very interested to hear about that. But before we do, it's probably useful for some of our audience to explain what the actor model is, because it is actually something that's been around for forever, right?
Yeah.
But not everybody is familiar with it, and it's making a huge comeback currently because of all the micro services architectures and trends like that. So can you give us a quick intro to the actor model?
Sure thing. So the actor model, to put this in perspective, I think the actor model, the original academic white paper that expressed the idea, was written 2 years after the original white paper that invented the relational database was. So it's that old, goes back pretty into the early 70s. And the idea in the early 70s was that the way most industrial sort of computers are going to be designed was, rather than having a small number of extremely fast CPUs, we were going to have a large number of very cheap ones. And that never ended up happening. That's not how hardware evolved. We ended up with a small number of cores that had very fast clock speeds, that had additional levels of caching and so forth. So the actor model didn't really take off. In the late 80s, though, an engineer named Joe Armstrong invented the Erlang programming language, which was sort of the very first real usable implementation of it. And he built it to try to develop, I think it was cellular phone networks and that sort of thing for AT&T and other companies that wanted to have a reliable, fault-tolerant way of handling massive amounts of information over a distributed system. And so the actor model's sort of core idea is that you essentially have an actor is an atomic unit of code, kind of like how a class is an atomic unit of code in an object-oriented system. But every single actor is also kind of its own independent microprocess, where it has a concrete life cycle where the process starts and you have some initialization logic. Then the process is in a running state, and I'll get back to that in a second. And then it also has a shutdown and a restart sort of state too, where you can go ahead and restart the process. So now what the actors do when they're in their normal running state is it's a message-oriented programming model, where all actors really do is you basically send an actor a message. An actor will go and do some work. So that might look like an actor might go and request data from maybe another actor and then combine that data with its own and send a reply back to the original sender. Or maybe the actor will go and execute some sort of routine where it fetches data from a database or something like that. The work that an actor can do is essentially the same thing that any other piece of code can do. The difference is that actors are designed to be isolated from each other. So if one actor crashes, that exception doesn't get propagated to anyone else. So you have really good error isolation on actors. The other concept that makes them valuable is actors exist in like a family tree structure. So think of like an org chart of actors. So there's a parent and there's children at any given point in the actor hierarchy. If a child fails, and in this case, failure means it throws an unhandled exception. Throws an unhandled exception, the parent up above it will get notified that the child failed, and it'll have an option to either tell that actor to restart, where the actor essentially reboots itself into its initial state again, and it doesn't lose any of the messages that it hadn't processed yet when it does that either. So it can pick up where it left off and keep going. Or the parent, if the error is so bad that like there's been a catastrophic failure that the system can't recover from, the parent can go and escalate that failure up to its parent. And you can have like a rolling restart of that whole portion of the actor hierarchy potentially. So the idea behind that concept of the sort of these independent processes that communicate via message passing is this ability to build what's called a self-healing system, where what engineers have found, particularly in distributed systems, is that you're going to have more consistent, predictable, and generally performant behavior if rather than trying to write a whole bunch of nasty code inside a catch block to like dig yourself out of an exception or a faulted state, you're better off just rebooting the failed piece of code into a clean state if you can. So the clean state's usually defined as the initial state of the actor. Then the last thing that makes why they're making a big comeback is actors are big on this concept called location transparency. So Bertrand, if I went and called your cell phone, do I need to tell AT&T how to explicitly route every single packet from my apartment here in Los Angeles to your office in Bellevue?
Well, no.
No, exactly. Your cell phone number is an example of something that has a transparent location. AT&T's network will maybe not AT&T. They're probably not the best example. Sorry, kind of digging at them to some extent. But any cell network will go ahead and translate your cell phone number into a route that my voice and data packets will follow. Actors have the same principle. You don't actually call a method like directly on an actor. You send a message to what's called an actor reference. It's like a handle for an actor. And that actor reference can be transparent across the network. You don't really need to know as a programmer whether the actor lives in memory in the process that you're currently running, or whether it exists remotely on another machine in your data center. So the advantage of that property of location transparency is you can build systems that can dynamically scale up the amount of hardware they have and scale it down. And you don't have to go and write a whole bunch of configuration management or glue code to go and do that. The sort of programming model inherently sort of provides cover for that for you as an engineer. And so what really has brought the actor model back, in my opinion, is that there's been a huge surge in the amount of data our applications need to use to be effective. And end users, because of mobile devices and the fact that we're much more connected in real time now, demand like real time turnaround on a lot of those results. So the combination of those two factors and the advent of cloud computing, where it's easy to get new hardware on demand, has really made the actor model a very viable option for that. So some of the companies that we work with at Petabridge who are using the actor model include big IoT shops. So people who do things like fleet and vehicle tracking, or we have some customers that run power plants and oil and gas where they're getting sensor data back from devices out in the field. Insurance companies that need to go and turn around like all sorts of different little customer-facing decisions quickly. Banks. Gaming companies is another big one. So there's like a million different use cases for it.
Excellent.
Yeah.
I was checking the questions window. We don't have any yet, but I'm sure we'll get more. Usually we get the questions near the end of the show when we don't have any more time.
That's all right.
Okay, so do you think that the resurgence of usage in actor models also has anything to do with the drop in network latency that is happening right now, where remote procedure call used to be something that was kind of scary for applications, but nowadays you can actually build distributed applications with much lower network problems and latency. So was that a factor?
You know, I would say to some extent, maybe from like that probably drove some more of like the business driven cases around the actor model. From a technology standpoint, the actor model is kind of designed to tolerate network failures, or so that's the idea in the CAP theorem, partition tolerance, right?
So what I meant was more for some applications, you wouldn't even have built it in a distributed way at all, without more reliable networking.
Oh, I see what I mean. Yeah, I think definitely the improvements in network hardware have definitely helped a lot. I would say the biggest one is that in general, most systems are designed to have a lot more bandwidth on their interconnects now. So that makes it possible for you, if you're using the actor model, typically you're sending a large volume of fairly small messages. But the concern there was that if you're doing that and you start running into issues like saturation or anything else, it can become a really big reliability issue. These days with like 10 gigabit Ethernet connects and all that sort of stuff, that I know there's some Azure boxes that are like prototype ones that have some of that now, I think. But with the advent of that stuff, it's becoming less and less of an issue. So like the capacity of our network has grown like really dramatically in the past few years. So yeah, I think that's definitely helping a lot. I'd also say in general, the connection between like the last mile between end users and data centers now is getting a lot better too. So I think there's a lot of improvements all around that are making like real-time apps sort of a little bit more economically feasible for everyone.
Yeah, it seems like in some applications, at least, IOs are becoming. It used that IOs were the limiting factor, whether it's reading disk or getting info from the network. But there are lots of applications now where the limiting factor actually is CPU and the local network throughput of the machine. So yeah.
Yeah, I've also seen issues where a lot of the times CPU bound applications. I think typically if your application is CPU bound, that's actually an indication you've done something right, because it means that you're basically going, well, you're assuming that you're only CPU bound. If you're everything bound, then you just need more hardware. But if you're CPU bound, you've basically gone and taken care of any egregious memory consumption issues. You're not wholly dependent on disk and everything else. That's typically a good indicator. One thing I've seen come up as a problem for some of these bigger applications is actually their databases often end up being the bottleneck. In particular, a lot of organizations have had, so I'll share like a user story real quick. We've done some work with some companies that were started off as these like CRUD.NET applications built on top of IIS and SQL Server like 10 years ago. And since then, the iPhone was invented and everyone wants to be able to get their stuff on mobile now. And there's all these new business cases and their technology stack has kind of stayed. It's been on better and better hardware, but it hasn't really changed. And SQL Server ends up becoming this horrible point of contention for all the different things that's happening in their network. So I've seen that quite a bit. And I think a lot of engineers and architects have sort of realized that and are coming up with architectures to sort of help spread, I guess I'd call it spread the rights around a little bit. So that's typically where the problem occurs. And the actor model has been one architectural way of solving that problem. But also there's a lot of investment in things like Apache Cassandra and NoSQL too. So yeah.
So in the actor model, you have a lot of messages going around. So is something like AkkadNet also playing the role of a message broker and message router?
Yes. AkkadNet is kind of designed in this way where the core Akka module just gives you actors you can use locally in memory. And there's people who will do things that use AkkadNet actors inside like a WPF or client application, right? Because it's actually pretty easy to, some of the same things you might use reactive extensions for can also be done with actors because they both implement that sort of reactive design style. But if you want to start using some of the modules like Akka.remote or Akka.cluster, it also gives you the ability to start actually distributing messages over the network. We even have a module that we just shipped an alpha of a couple of weeks ago called cluster.tools. And that includes something called distributed pub sub in it, where you basically can have actors somewhat transparently over the network publish and subscribe messages to each other. And that's one of these cases where you kind of have like, that'd be kind of the equivalent of like a big message broker technology, but it's done in the sort of distributed fault tolerant fashion.
Okay. A couple of weeks ago, we had the people from NATS on the show. I don't know if you know that technology. It's basically a message broker technology that scales really, really well. Is there a way you can make both things work together? Like you choose your message broker to be some very specialized and performant technology, and then you program on top of it using an actor system.
Oh yeah. Yeah, absolutely. I presented at End Service Bus's conference back in December, and they're another example of a technology in that category. And one of the things I told them is like Akka.net, while it can do a number of the things that a message broker or a message bus can do, there might be some features that one of those technologies have that you really like, or maybe you've had a really good experience using it in production and you don't want to move away from it. What you can do is basically you can put Akka.net on either end of that, basically as a message producer or a message consumer, and just have it go and pull messages off the queue and have that be the way that data sort of comes into your actor system. We have a lot of customers who have used, in particular, the one I see all the time is RabbitMQ. So they're using like RabbitMQ with mass transit on top of it, and they really have a good, reliable system that produces messages. But what they wanted to use Akka.net for was simplifying the concurrency management and everything else on the consuming end of that queue. So they would go and maybe refactor the consumers to be like an Akka.net cluster on that end. So
it gives you a better programming model on top of those technologies.
Yeah, exactly. One of the things that's particular about the way actors work is the enemy of traditional message processing systems is that you have to do write a lot of your own code for managing concurrent messages happening in lots of different places, either within one process or across multiple processes. With actors, you can process those messages asynchronously and concurrently without needing locks or synchronization mechanisms. And the reasons for that are there's three sort of design traits of how an individual actor works that allow it to be able to essentially be an atomic thread safe unit. The first is that actors only process every individual actor only processes one message at a time. So when you're processing a message, you have what's called a receive handler. This is like a little lambda that says, for this type of message, we're going to go ahead and execute this function. Whenever you're inside one of those receive handlers, you're not going to be processing any other messages until you exit that method. So everything you do to modify your actor state is thread safe. The second is that all actor state is private. It's never shared. It's not accessible via properties or anything else like that. So you don't have to worry about someone else side affecting your state. And then the last is that all messages are intended to be immutable. So if you're not familiar with the concept of immutability, a string is an example of an immutable object in .NET. If I go and call the toLower function on a string, I'm not modifying the original string. I'm creating a copy and modifying that and returning it. So that means that I can go and share a piece of data with another actor via message. And if they go and modify the contents of that message, it doesn't modify my state. So all of that means you can process lots of incoming messages concurrently without having to use synchronization mechanisms or any of that gnarly stuff.
Yeah. This is not specific, by the way, to actors, of course. A lot of concurrency code nowadays is done this way with immutable objects and communication channels and internal state that doesn't leak out or anything. Yeah, sure.
Yeah, the mailbox processor in F# that's built directly into the language is another example of a technology that does that.
Yeah. And in Go, it's the default pattern to do concurrency as well. And yep. Okay, so we have some questions here. One is from Sahin. can you explain AkkadNet and microservice correlation? Can we think of AkkadNet as an implementation of microservices?
Man, that is a great question. So yes, you can think of AkkadNet as a way to implement different microservices. And the way that's done is through the Akka.cluster module. And that's one of the modules that I work on directly. And what the cluster module is it's a way of building a Dynamo style cluster. So if you're not familiar with Dynamo, it's DynamoDB, which a distributed key value pair database that Amazon invented. Other technologies built on that clustering model include things like Cassandra, React, Voldemort, you name it. The way those clusters are meant to be designed in Akka.net is they're supposed to be heterogeneous, where you can have multiple different Akka.net applications that communicate with each other through the cluster protocol. And the way you distinguish them is in your configuration, you can specify a role or one or more roles for your nodes. So if I have a web front-end node that uses, let's say I'm using SignalR and ASP.NET MVC to go and send some data back to my end users, I can designate those services as web roles. And then if I have some app servers that, let's say I'm doing some stateful like data accumulation, like if I'm running a chat room or something, I might have a little Windows service that accumulates all the data for each individual chat, for one or more individual chat rooms. I can go ahead and have the web roles communicate with a chat role just using what's called a router, which is a special type of built-in actor in Akka.net that just distributes messages. And there's clustered routers that can go and direct messages to specific roles. So you can specify that all in configuration. And that's a way of implementing microservices there. So that's probably the most concise explanation for that.
I see. And I had a question about the way the messages are routed. I was curious about do clients, how does it happen? When I create a message, do I have to know who is going to handle that message, or do I just, emit a message and whoever can handle that message just takes it and treats it? Does that make sense?
Yep. So there's two. So basically, to send a message, there's two ways to do it. One is you have a reference to the actor you want to send that message to. So you have basically it's like a pointer to that actor, and you go ahead and tell that actor reference a message, and the actor will receive it. And the actor can choose not to process it. It can choose to forward that message onto someone else who will respond back. So there's some transparency around who can actually handle it. So that's one way. And then if you send a message to a router, by the way, that's exactly what's happening. You send a message to a router and it goes and forwards that message down to a concrete user-defined actor who handles it. The second way,
in some cases, it's not that you send it to a specific actor. You do send it to a specific actor, but whose role is to hide the fact that there are going to be other actors that are going to be able to party on that data.
Yeah.
Right?
Exactly. The actor model sort of has this idea of like extremely loose coupling and routers and sort of the transparency of like who's in the hierarchy underneath the actor you're talking to. You basically generally aren't supposed to be aware of that as the programmer. The other way, if you need to explicitly communicate with a specific actor, every actor has a globally unique address within a cluster. And so that'll look like a combination of, if you're using a cluster, the protocol you're using, so akka.tcp / the name of the actor system. And then you have like the IP address and port, and then you have a path of sort of where it starts with the root actor, then the top level actor, then the child, grandchild, great-grandchild, etc. So you can explicitly address an actor via what's called an actor selection. And that will allow you to go and send a message to, even if you don't have a reference to that actor yet, you can go ahead and look them up by their address, essentially.
And so if that's the case, if you do that, what happens if that actor reboots?
Well, if the actor reboots, it's still going to be at the same path. So when an actor reboots, like sort of the way the actors are designed is they sort of have three component parts. You have the mailbox, which holds all the messages. You have the actor class that you defined, and there's this thing called the actor cell, which is sort of a fabric between them. the actor cell and the mailbox never get, the actor cell is what holds the address, and that never gets touched on a restart. The only thing that happens is that your current actor, like your current instance of your actor class gets destroyed and recreated using the form. There's a formula for how you start an actor. It's called props, because it took me a year to figure this out, but it's called props because every actor needs a prop to act. Anyway.
Oh, okay.
it took me a year to figure that out. But basically it uses the props that were originally used to create the actor to basically recreate it from scratch. So
what exactly happens to its state when it?
The internal state gets destroyed. You have an option. You have some what are called life cycle methods. You can run what's called a pre-restart method, where basically you can go ahead and take your internal state and maybe send it to yourself as a message, which works. Or you can go ahead and there's another library called Akka.persistence, which allows your actors to journal their state using event sourcing to a durable store. So when the actor restarts, it'll go ahead and replay all the events that it saved and recover.
Okay.
Yeah.
Yeah, I was going to ask what kind of state is it reasonable for an actor to actually hold? Is it that it's transient state that just lives for the lifetime of a message, or does it have more persistent state? And you kind of answered that.
I've had actors that accumulate state for months, where basically they're sitting there and they're constantly totaling up data. And those actors, by the way, when you're holding on to state for that long, the way you sort of work with the database generally in Akka.net or any actor model approach is the actor's single source of truth is its in-memory state. The stuff that it writes to the database is a hard emergency break glass. You know what I mean? It's not meant for...
Actually, I don't, because you were cut off for a few seconds here. So can you say that again?
Sure. So I was going to say was actor's internal state, you can hold on to it for an arbitrarily long period of time. But the general rule of thumb with all actor implementations is that the internal in-memory state of the actor is a single source of truth. Everything in the database is a cold backup. So what actors will typically do is they'll go and maybe like journal their state or their state changes to a durable store like a database or Azure table storage or something like that. And then they'll go and recover it in the event of a crash or in the event that they were stopped and started again later. So it's really up to you. There's really no right or wrong answer to doing that.
Yeah, it's not like on the web where everything is supposed to be stateless. And
in general, one of the huge benefits of actors is that they can be stateful. So you're able to go and do things like process a stream of events for one user and be able to react to how those events change over time. And so the other things that you'll see a lot of people do with actors is they have this, at least in Akka.net, they have this concept of a scheduler, which is you can go ahead and schedule like automatically recurring messages to yourself or someone else. And so what a lot of folks will do is they'll design actors in order to like keep their memory footprint bounded. They'll design it so if an actor stops receiving messages for longer than some window of time, usually like varies by application, but in my case, I've done like 60 seconds. That actor will go ahead and do a final persist of all of its state and then shut down. So that way, the only actors that are available in memory are the ones that are actually doing work at any given time. So that was the difference between me keeping like 2.5 million actors in memory versus 25,000 at any given time, was basically just having a smart sort of last recently used algorithm for cleaning them up. And that only takes a few lines of code to implement. So
and when you need to revive it, how long does it take?
When you need to revive it, it goes into, so one of the other things that actors can do, by the way, is they have the ability to switch their behavior. So based on some message they receive. So here's a good example of when you might want behavior switching. Let's say you have authentication built into your application as a feature. The way you handle messages from an end user before they're authenticated or after they're authenticated might be very different for the same type of message, right?
Yep.
So what I would do in that warm-up state is I'd have a behavior where I was waiting for data to come back from, in this case, I was using Cassandra. I was waiting for data to come back for it. And as soon as I got it and it passed a health check, the actor would begin processing normal messages. And that process took like 40 milliseconds or something like that for it to go and do that. And most of the time there was the round trip time to get stuff out of my database. So yeah, the actual work itself, like individual actors in Akka.net, we've benchmarked them, are capable of processing like up to millions of messages a second in memory. So over the network, obviously, there's a lot more work that goes into delivering a message. We have to serialize it and then put it on the transport and then get it off the transport and then deserialize it again and then route it. So there's a lot more to it there. But in general, actors in Akka.net are very fast in terms of what their message throughput is.
Great.
Yeah.
Matt is asking, you mentioned processing 500 megabytes of data per second. Can you talk more about the infrastructure you used? For example, server specifications.
Sure. So I actually have a blog post about this stuff on my personal website where I describe the architecture we used for doing that. So that 500 megs of event data per second was measured by our load balancer. So that's the raw HTTP sort of payloads coming in. By the time we got it into a state where it was going to be written to the database, we aggressively compressed that. So it probably we probably shrunk it down by at least 100% in terms of, well, like down from like, sorry, that's not the right math. Down from like 500 megs to 5 megs, something like that. So we were using Amazon Web Services, Elastic Beanstalk. We would have about 6 at peak loads, like around that time, we'd have 6 of their, like I'd say bigger, medium-sized servers, the ones that had 4 cores and I think 16 to 12 gigs of RAM, something like that. So that was sort of handling the brunt of the work. It would go and do some work and it would save some, that was our original sort of analytics application, which would just CRUD stuff directly to Cassandra. It would go save all that work to Cassandra and it would go and basically pull out the relevant messages that needed to be sent to our actor system. And by the time those messages got put onto the wire, there'd probably be, I think we were probably doing like 7 or 8 megs a second going over all the TCP connections that we had. So it compressed very well. HTTP is extremely verbose in terms of like how big the footprint of it is. And then the actual Akka.net servers we had were much smaller than the web servers. They were 2-core, 4 to 6 gigs of RAM, and they were running at about between 10 to 30% CPU utilization during peak hours. And internally they were processing something like 10,000 messages per box per second. So now, and we didn't measure every single message we sent in there. We only really measured the ones that were sort of at the very front of the propagation chain. All the little sub messages that went into that we didn't instrument because measuring those added more overhead than processing them. So like the monitoring overhead was greater than the amount of work that was happening. So we went ahead and removed it. Plus, in general, when you're dealing with like monitoring a live actor system, once messages make it from one end of a service boundary to another, and all the messages are happening internally within one process, all the message delivery is being done in memory, and there's no more serialization inside Akka.net, and there's no more of any of the other sort of risky stuff. So it's pretty safe once it's made it from one end of the network to the other. So I didn't bother monitoring any of that. Only things I really monitored was sort of stuff going into one service and coming out of another was typically what I did.
Can you talk a little bit about scaling out and load balancing?
Sure. About Akka.net or about that architecture I was talking about? Okay. So for Akka.net, so one of the things that Akka.cluster can do, so I remember I mentioned it's built on this Dynamo style of clustering. One of the things that's special about that is it's essentially a peer-to-peer network of servers. There's no single point of failure or single point of bottleneck. But there's a protocol that all of the nodes can follow that allow them to essentially dynamically join or leave the cluster. So the way it works is you have this concept of a seed node. Think of this as a node that lives at a well-known IP address and port that is reachable by any new member that attempts to join. And so typically what we would do is I have another open source project called Lighthouse, which is like a very stupid Akka.net cluster node that never needs to be upgraded, essentially. All it does is it runs top shelf and Akka.cluster, and that's it. I'd have a couple of those guys running on some static IPs that don't ever change. And the rest of my services would go ahead and connect via essentially like Elastic Beanstalk, or maybe if they were stateless, I'd probably use something that would be elastically scaled up and down. So an auto-scaling cloud service or Beanstalk. I would go ahead and basically have them dynamically join the cluster by contacting those seed nodes. And then when they're ready to scale down again, I would listen for that event coming in from, AWS will send you a webhook or something when the cluster is going to scale down. And I think Azure has some equivalent to that. You'll go ahead and get a notification that basically, oh, this machine's going to go offline. So you can go ahead and basically have that node remove itself from the cluster. So the cluster membership basically drops it, and then the cluster size will shrink down again. For stateful nodes that are actually keeping in-memory state, generally speaking, depending on how much data is clumped in each node at any given time, you want to auto-scaling a data node is much more risky. It'd be kind of like auto-scaling a database, right? Use caution. So for those stateful services, typically I would manage those manually when I need to scale them up and down. Ideally, the way you want to design an Akka.NET cluster is that your stateful services, even under extremely high bursts of activity, have enough headroom in the amount of servers they're running on and are designed in such a way that they only gradually increase their resource utilization. You want to put most of the scary work that happens into stateless services that can be easily scaled and replaced. So for instance, we had someone prototype a video processing system with us, where they were looking at taking these sort of raw, like uncompressed 2-hour-long Hollywood movies and then turning it into like 30 different formats for all the different devices out there, applying closed captioning, applying DRM and all that stuff. These services that were stateful were the ones just coordinating the work that was happening, and they used virtually no resources. All the boxes actually doing the crazy video compression and transcoding and all that, those were stateless. So that's an example of like a correct design, essentially. Because if one of those stateful servers fails, let's say, and this isn't outside the realm of possibility, oh, there was a problem transcoding this video file because this machine had some other background process that kicked off and it ran out of memory. It's very easy for that stateful service to go and tell a separate node of the stateless one, restart that job. If a stateful service goes down and you have to go and figure out what were all the different things that was processing, and you're trying to recover that from a durable store, the cost of something going wrong there is much higher. So that's why you want to typically design it in such a way where you shouldn't have to auto scale it. There is a new module we just shipped an alpha of as part of the last release called cluster sharding, which gives you the ability to have shards and replicas of your state elsewhere in the cluster, which makes it a little bit less risky. So that's sort of, I guess I'd call it data integrity by means of duplication, where you have, sort of hot copies of it running elsewhere. That can help a little bit if you have a lot of data you need to keep in state and you really do need to dynamically scale up and down. And there's another module that we haven't finished yet that we're working on called distributed data, which is an in-memory, sort of does the same thing that cluster sharding does, but isn't persistent. So it's all done using like an in-memory distributed key value store that's eventually consistent.
Nice.
Yeah.
We have another question from Matt that is actually not on AkkadNet, but on NBench.
Okay.
The question is, what aspects of performance does NBench measure? What assertions are available?
Okay, that's a good question. That reminds me, I'm supposed to do a new release of NBench, and I haven't done it yet. So NBench is designed right now to measure 3 things primarily. And we wrote NBench, by the way, to solve a problem with Akka.NET, which was contributors would send in pull requests, and we ended up having a regression where some of the changes that we merged inadvertently affected performance. But we actually really in a lot of detail, reviewed that code first. But even in Akka.NET developers, we're pretty good. We've been doing .NET for a long time. But even with our just with our human knowledge and our cumulative years of experience at .NET, had no idea the performance impact that code would have. So we decided to instrument all pull requests going forward with automated performance tests to verify that there wasn't a regression of that nature again. So NBench was designed to tackle 3 specific ones initially, but I'll tell you about what we're going to do to make it more extensible down the road. Throughput is the biggest one. Simply stated, if you have a block of code, how many times per second can that code be run on the hardware you're benchmarking? So if you have a function that does something really trivial, you might be able to run that 150 million times per second. If you have a function that uses a database connection to go and write some stuff to SQL Server, you might be in the neighborhood of thousands of times per second. So that's the idea there. The second thing that we measure, and our way of measuring this is very coarse-grained right now, is memory allocation. So how much memory did this block of code use? We use the garbage collector to get that data right now. So it's not very precise. The best practice for doing that is if you want to measure how much a particular class allocates, go ahead and allocate about 10,000 of them and divide whatever the number we give back to you was by the number of instances. And that'll get you a more accurate measurement there. So we use the garbage collector to do that today, although there's more accurate tools out there. Like JetBrains has a really good NuGet package they released that allows you to profile objects using a much more deep type of introspection. And the last thing that we measure is garbage collection. So when you run a block of code in an NBench test, how many generation 0, 1, or 2 garbage collections occurred. And the reason why you care about that is if you have a lot of code that's doing generation 2 garbage collections, you're going to experience a lot of pauses inside your application where we're going through and collecting those objects, and that'll hurt your throughput. So you have the ability to go and decorate your tests with attributes to measure all or one of those if you want. You also have the ability to
it also makes your latency less predictable, right?
Yes.
Because you don't know when those pauses are going to happen, and that might affect some of your requests and not others, and that's unpredictability that is often not something you want at all, right?
Yeah, absolutely not. The more stuff your application does, the more harmful that becomes. So the general rule of thumb is keep everything in generation 0 or put it into generation 2 and have it live forever. So that's sort of the general rule of thumb for that stuff. One of the things we're going to add in the not too distant future is we're going to allow you to instrument any arbitrary performance counter as an NBench measure. So that'll go ahead and open up the doors for things like, if you want to go ahead and measure how many page faults you had or how much disk I/O this code used, you can be able to measure that going forward.
Okay, so is it fair to say that the basic idea of NBench is that performance should be part of your continuous integration?
Yes, it is. It's the idea is that if you're building like highly available systems, you need to know your components that are on the critical path. So the 20% of your application that's being called 80% of the time, you need to have a pretty clear idea of how every change of those components affects its output, essentially. Because the last way you want to find out is with angry customers. Yeah,
exactly. You want to catch those early. And so the next question I would have about that is, in the same way that unit testing is not going to test interaction with a database, for example, how do you deal with the fact that a lot of performance testing is actually relying on the actual infrastructure and not just on what the code is doing, right? It's not CPU bound oftentimes. It's more.
Well, I have some plans in mind for how we can eventually do, I guess I would call it system-wide load testing, essentially, using like a distributed version of NBench. That's kind of long-term sort of thinking right now.
So it's to NBench what functional testing would be to unit testing?
Yeah, think of it as integration testing where a server dies at the end of it if we've done our job right. So one of the things that I did when I rolled this myself, and unfortunately it's not open source. But one of the things that I rolled myself at my last company was, and this is built on top of AkkadNet, was a system that would intercept about 1 to 5 minutes worth of our live HTTP traffic, and we would go ahead and serialize all of it to disk. And I could go and replay that over our test infrastructure every time we made a change. And so it would simulate like live traffic essentially. And originally we used that for debugging, but eventually it became a load testing tool for us too. Because I could do things like play every request 4 times or something like that. And I could go ahead and amplify the amount of traffic if I wanted to dial it up. And that would also correlate to what our live traffic patterns looked like. So that's the idea of, I actually stole that idea from MMO game designers who said the only way to really load test their systems was to run saved games. Because that had all of the weird human introduced sort of variables that you can't account for in a simulator that's written by a programmer that arbitrarily comes up with stuff. So I want to do some. I want to basically reintroduce a technology like that and make it open source. So that's a little bit more. I've got too much on my plate right now as is, but that's what I want to do eventually. Okay,
so Sahin has another question, which is what happened to AkkadNet and Packet Package Manager? Can you give details like pros and cons? I have to say I don't know what this is about, but I'll let you.
Oh boy, I'm setting myself up to earn the scorn of the F# community here. Basically, what happened was so Packet is an alternative to NuGet, and we have a lot of very strong F# developers who use Akkad.net, and they pointed out how Packet would help us solve some problems that were, in my opinion, fairly minor with NuGet, but still there were problems. So I was like, oh, okay, we're open to doing it. But the problem was synchronizing NuGet dependencies across all the different projects in our solution. Essentially, it was the thing that Packet was trying to solve. And the issue with Packet in our case was, if you're going to have a better mount, like imagine this. I go ahead and someone sends me fork 2.0. It's a brand new fork, and it is a vastly, it's a better fork than what my current fork does. But every time I invite people over for dinner, I need to have a 4-hour-long training course on how to use it. And sometimes the fork has some issues or it does some things that are unpredictable, but it does solve some problems. Are you really going to use fork 2.0, or are you just going to stick with the fork that already works because it's a fork? That's sort of how I looked at Packet versus NuGet. Is like, you know what? The problems that the Packet introduced more problems than it solved, basically. It would go and glob up our solution with thousands of lines of XML configuration stuff, which made it very difficult for me and the other core developers to review pull requests. And I couldn't figure out, after spending an hour going through their docs, how to upgrade one of my own dependencies I needed to manage. So it was one of those things where it's like, I get the F# community is real passionate about developing tools and everything else, but Packet is just horribly over-engineered for what it's trying to do. It's just a matter of really just a matter of, to me, as terms of how I value my time as sort of an engineer and a release manager for Akkad.net, did not provide nearly enough benefit for me to keep using it. Because the thing you got to take into account when you introduce a tool like that, anybody else, do I really want to take on the cost of training every new person who wants to go and modify a NuGet package when they're contributing to Akkad.net and how this tool works? The answer is no. I don't want to take that on. So it's not good enough. It's, in general, for software developers, building a better tool isn't good enough. It has to be a better tool that solves a problem in such a way that it's worth the cost to go and learn how to use it. And Packet failed that test for me.
Okay.
So, yeah.
Fair enough.
Yep. So yeah.
Okay. So earlier you mentioned something about Java and .NET.
Oh yeah.
So let's go back to that.
So yeah. So Java concepts not expressed easily in .NET,
yes,
and vice versa. So okay. We'll talk about Scala specifically, because that's what the Akka is implemented in. So Scala is kind of like how F# is implemented on top of the CLR. Scala is implemented on top of the JVM. Same idea. And Scala and Java have the ability to interoperate with each other too, kind of like how F# and C# do. Scala has a very useful concept built into it called traits. And what traits are specifically is, think of it like an interface you can implement on a class that already has static methods built into its handlers, essentially. So if I wanted to go ahead and add a trait to one of my classes that would automatically, log something or something like that, I could go ahead and bolt that on, and I don't have to implement the method. It's already done for me. So it's basically interface with a default implementation. So Scala Traits basically take the idea of interface composition to the next level, in my opinion, where you can actually go ahead and have traits that go and bring implementations with them too. I don't think traits have the ability to be overridden. So there's no idea of a trait with a virtual method. It's more just like bolting on a capability to a class, essentially decorating a class with additional methods. So and because Scala Akka sort of depends on that through a lot of its object model, the way it's sort of defined a lot of its internals, having to express that in C# using our inheritance model was much more difficult. But we were able to figure it out eventually. So that was one way of that was one big difference. Another one.
How did you implement it?
How do we implement it? I think we had to get very creative with how we did base class inheritance. We'd have to go ahead and say, okay, what's this trait that gets commonly used amongst all these actors? Okay, we're going to go ahead and declare a new base class, put that on there. And then we also came up with a somewhat aspect-oriented way of doing what's called the actor creation pipeline, where if you went ahead and decorated an interface, decorated an actor with a specific declared interfaces, we would go ahead and dynamically populate the field that interface adds with an implementation. So that's how stashing works in Akka.net, for instance. So we sort of used a couple.
So it sounds like a more composition-based approach. It sounds a little bit like mixins as well.
Yeah, it's exactly
like aspects. So.
Yeah. So we basically did a combination of those two things, and that worked pretty well. And then in other areas, I think we just straight up had to violate the dry principle one or two times, where that was like, after exhausting all other options, that was just the only way to do it. And I can't think of a specific example.
That makes me think of, Go has some proverbs that express, the spirit of the language and so on. And one of them is, it's better to copy a little than to get a dependency or something very close to that.
Yeah, exactly. We in this case, it was cleaner and safer to go and repeat ourselves than to add a dependency on two objects that had no relationship to each other. So that was one. Another issue we've had, reporting Akka streams right now, which is an implementation of the Reactive Streams specification. And I mentioned earlier that the JVM has very weak generics. Whereas .NET has probably the best generics implementation out there. Well, one disadvantage of having good generics is that there's all sorts of illegal and frankly unsafe casts in .NET that are perfectly allowable in Java. So for instance, if I have an interface that takes two generic parameters, let's say types T and S, in Java, I can go and directly cast that to an object of type, same interface, object.
Because it is actually the same implementation underneath, right?
Yeah, exactly. So I can go ahead and make that cast. And so the Reactive Streams stuff inside Akka leverages the hell out of that sort of language design. So trying to express that in .NET has been this exercise in frustration for the 3 or 4 people who are working on that so far. And I had to deal with some of that myself working on .NETty and Helios too, which are also ports of Java libraries. So there's so that's another concept where it's just like the relative lack of type safety with generics in the JVM gets used there to do certain things that are much more statically type safe in .NET, but difficult to express. Requires a lot more compiler ceremony, sort of. And it's not necessarily a good or a bad thing. It's just we have what we have and they have what they have, so that's one. A thing that we have in .NET that they do not have on the JVM is we have a really good socket library setup. So we have really good out of the box asynchronous sockets. In the JVM, like they're dealing with pull and wait and all that sort of stuff, where it's they don't really have anything kind of like socket async event args in .NET. And so they've sort of had to hack their way around that a little bit. So that's something we had a little bit of an easier time implementing. I guess one of the other things that the JVM has that we don't is the ability to have instances of thread pools. So in .NET, we have one sort of static thread pool, right, by default. And that's all well and good, but what if you need to use, there's a concurrent programming concept known as exclusive scheduling, right? Where basically you need to have some threads that are available for the exclusive use of applications that either have a higher priority or maybe they need to be keep those lines open for being able to do interrupts or something like that. In particular, there's some mission critical systems inside the remoting and clustering infrastructure of Akka.NET that absolutely have to run on their own isolated threads. Because if you are using the default thread pool in Akka.NET, which all actors do by default, every single actor dispatch, every single TPL call, every single like all this list of stuff all use that same thread pool, and the work queue can get very large. So if you have a soft real-time programming constraint, and an example of what that looks like is in Akka.Remote, every single end of the connection must receive a heartbeat or a message once every 3 seconds, or the connection is considered to be faulted. That becomes a problem. So we had to go and implement our own dedicated thread pool implementation. And we have that available as a separate library in the Helios project. It's actually just a NuGet package that just adds an internal CS file to your app. So it's not actually an assembly. And we actually made some major performance improvements to that based on some of the stuff that was added to, I think, .NET Core's thread pool implementation, actually. So we had a contributor do that in the last patch. So that was another thing. Java in the JVM, you know how you have the notion of an execution context in .NET or synchronization context. I guess that's the idea, right? Every single thread has one. That's kind of an implicit context that flows automatically for you. You have to explicitly manage that on the JVM when you're working with your own threads. And so we were able to go and avoid all of that sort of boilerplate code in our own application, just because it's kind of done for you, which is nice. And then I guess the last thing I would add, and I'm probably going to catch some grief for this within the Akka.NET community because I'm known as the biggest async await hater in there, but actually having async await solved some problems, particularly when it came to doing unit testing for us. A lot of other languages are trying to implement that on the JVM and on other runtimes like JavaScript. But having that natively actually made it very easy to test certain types of things inside our application. So yeah,
okay.
We've had, to give you some context on that, Bertrand, we've had these epic flame wars over whether or not async await should be supported inside actors, because they kind of, from a conceptual integrity standpoint, somewhat async await within an actor, which is designed to be, synchronously process a message and then move on to the next one. There's somewhat of a conceptual conflict between those two ideas. We ended up coming up with a compromise that works, but still isn't the recommended way to do TPL stuff in Akka.NET. We recommend that people use the pipe2 operator instead, which is a way if you go ahead and have a task, you do your continuations, and then you pipe the final object that's produced as a message back to some actor.
That's very interesting, and actually I might follow up with you on this with some folks on the team who might have some interesting input into that. So
yeah, that'd be good.
We are horribly out of time, but here is one last question that I think is really important to ask. What is the plan for porting Akka.NET to .NET Core?
Oh boy. So we just talked about that in the contributor meeting this week. So the answer is that .NET Core perfectly aligns with Akka.NET's core user base. These are people we have some people building client-side apps, but overwhelmingly our users are building server-side applications. And .NET Core is really designed to be lightweight, deployed in a container on VMs that aren't necessarily Windows. So the debate that we have had internally about doing this is whether or not all of our dependencies, because bear in mind, like Akka.Persistence takes a dependency on we have plugins for Cassandra, Mongo, Postgres, SQL Server, Event Store, Azure Table Storage, Service Fabric, you name it. All of those drivers would have to be in .NET Core for us to fully port all of that. Plus, we also depend on .NETty, which I know they want to support .NET Core too. We depend on certain serializers. We depend on a couple of base class libraries for things like immutable collections. So we kind of have to go and I kind of look at moving to .NET Core. Like if I went and dug a hole in my front yard and that's AkkadNet now, and someone asked me to move it 8 feet in the other direction, so we got to figure out how to do that.
We're happy to help with that, by the way.
Well, thank you. I appreciate that. The answer is we want to do it soon. I think what we are trying to do in the short run is we're actually trying to clean up some of our dependencies. So we have sort of a final list of the things that we are going to have hard dependencies on going forward. So like we're going to be replacing our default serializer, getting rid of JSON.NET and using something that compresses better. And there's other stuff like that we're going to be changing soon. Once that's settled and we have sort of a clear idea of what all of our dependencies are, it becomes easier for us to plan on how to move. I think what we'll end up doing is offering one thing we might have to do is because we have some people who actually have AkkadNet running on Xamarin and Android right now, and it has the same problem .NET Core does, which is we depend on system.configuration for loading up a HOCON configuration, the configuration format that AkkadNet uses. And that's not supported in .NET Core or in Mono. I think it's supported in Mono, but just not Xamarin and Android. We basically are probably going to go and extract that, move it to a separate library that people can install. And then we'll probably ship a portable class library that supports .NET. Right now we support .NET 4.5. We'll probably bump that to 4 or 6 or maybe 4.52. One of the ones that has long-term support. Bump it to one of those and then also support .NET Core, whatever the first sort of stable version of that is. So
cool.
Yeah.
Well, this has been a fantastic podcast, I think. At least for me, I was very interested in everything you had to say. So I think I hope that also translates to the audience. I want to thank you again for being on the show. This was great. And well, thanks everyone who watched. And we'll see you guys again next week.
Yeah, thank you. And the last thing I wanted to say before we sign off is if you're interested in learning Akkad.net, if you go to learnakkad.net, there's a free boot camp there that'll teach you all the basics of the actor model, and it'll help you build like 3 applications with it. And so that's also on GitHub too. If
you have any links that you want to put into the description for the video, please send them and I'll add them.
Sure thing. I'll go ahead and send you links to everything we covered today.
Cool. Well, thanks again, and I'll see you later. Bye-bye.
All right. Thank you, Bertrand. All right. Bye-bye.